Enter chapter 2 is actually way later in our textbook, but deals with fragmentation of molecular ions, of mass plus peaks. This is important because this tells us what types of fingerprints we're likely to see for certain types of molecules, oftentimes related very closely to its functional group. The reason it's placed so late in your text is because we're always going to have the stability of a free radical as one of the factors for our overall fingerprint. But it actually follows the same pattern that we saw before for carbocation stability, so I'm confident that you can actually do this just fine. Just like we saw before, carbocations are more stable if they're tertiary, less stable if they're secondary, and less stable if they're primary, and actually fairly unstable if they're methyl. So like when we saw in our last set of slides, hexane fragmenting, we saw that the most stable ion was actually one that had both the cation and the radical as primary, which is the most stable fragments that we could form. It was much better than having a methyl radical, for example. And we also see that there's a difference in stability between sp2 and sp hybridized orbitals, and also between unconjugated and conjugated, where conjugated is much, much more stable. The same as carbocation is much more stable if it can be spread between multiple locations. Whenever we have a mass plus peak, it's going to generate new mass plus carbocations and uncharged radicals as it fragments. In this case, the stability of the carbocation is actually much more important to the overall stability. They're both still important, but the carbocation actually means more. And so that's also good news because you already know a lot about carbocation stability. And again, the most stable cations are the most visible, so our largest peaks come from the most stable cations that can be formed. So if we look again at our fragmentation of hexane, we saw that we had a mass peak up here at 86. This is our mass peak, or mass plus peak. And we saw that we have fragments that occur at, I think this is 57. We have a fragment that occurs at 71. And we see that this is much less stable than the 57 fragment. The 71 fragment would come, it's 15 lower than 86. It comes from shearing off a CH3 group, 12 plus 3 for 15 total. Mass units come off when a CH3 comes off, and we'd have a methyl radical. But because the methyl radical is significantly less stable than a primary radical, we're a lot more likely to shave off a CH2 and a CH3 and have this be our major mass product. And so we see that that's actually true. If we shave off a CH2 as well, then we go 14 lower, 12 plus 2 for the hydrogen, for a total difference of 29 between 57 and 86. So this 57, it corresponds with this unit. We see that the fragmentation pattern will change if we have an isomer of the molecule. So we can tell a lot about the carbon skeleton from looking at it this way. Notice that we actually see an even lower mass peak. That means the molecular ion is much less stable in comparison to the major peak. And we still see that same peak at 57 from having a CH2, CH3 group pulled off, like maybe this, but it's not nearly as prominent. And we see the 71 peak actually being higher from pulling off a CH3 group. Well, that's because if we pull off a CH3 group, that 71 peak right here, sorry, the other one was 57. The 71 peak is from shaving off a methyl radical here or here. And while the methyl radical itself isn't very stable, it would leave behind a positive charge here, and that positive charge would be secondary rather than primary, much more stable. And since the carbocation matters more than the other radical, we're actually in much better shape. It's even better if we shave off this entire group though, and then we end up with a secondary carbocation. If we shave off another 14 right here from the CH2, to go us 14 lower than 57, we end up with a 43 peak, and that corresponds with these carbons over here with a secondary carbocation. Again, much more stable than the primary carbocation. Sometimes we see fragments that are so stable that we don't see the molecular peak at all. So this is actually an isomer of our original molecule. We have the 86 here. It's still isomer of hexane, 6 carbons, but we don't see that 86 peak. We do, however, see really significant peaks in a bunch of different places. One of the most significant of which is taking off these 2 carbons. Taking off 2 carbons would give us a tertiary radical, which is really stable. We can also fragment a couple of other ways and end up with other super stable fragments. So when we have things that could be like tertiary carbocations, we're a lot more likely to have the mass peak disappear altogether. So it's worth noting that our biggest peak isn't always our mass plus peak. This is not a mass plus peak because there's actually a missing peak from that superstable fragment. We can tell because we have a lot of ions that are of really high relative abundance. That's probably what's going on here. We talked about in our last section that typically the electrons that are ejected are the ones that are at the highest energy in the molecule. And we said that that's typically carbon-carbon sigma bonds in an alkane. We have lots of different functional groups that actually have different highest energy electrons. In this case, we have a pi bond in this alkene, and those pi bonds, that actually looks like an extra bond, I'm going to erase that. Those pi bonds are higher in energy than most other electrons. When we eject a single electron from a pi bond, we get one side that's a carbocation and another side that's a radical. And that leads to interesting possible pathways for fragmentation, because we can stabilize this carbocation through a specific type of falling apart for the molecule. We see that happening because the radical can actually feed into a double bond if we pull out an electron from a neighboring single bond. Radicals are very reactive, and so until we talk more about radical stability, nothing should really surprise you. In this case, if we pull out a single electron, notice the arrows only have one side, meaning they're only moving one electron. If we pull out that single electron, we can end up with a cation that's resonance stabilized and still a primary radical as part of that stability. That ends up being really, really stable, and so we'll see very dominant ions that are formed essentially at the allylic position to a double bond. So we'd say if we had a double bond that was originally here, we'd break off between the alpha and beta carbons to that. So this would be like an alpha beta cleavage, and that could be really indicative of a double bond. We have that same type of cleavage if one of the double bonds that gets ionized ends up being on an aromatic. We still have that same movement into stabilizing the positive charge in a double bond over here by pulling an electron from the over here by pulling an electron from the neighboring carbon here. When we do that, we end up forming, again, a radical species that doesn't matter nearly as much, and we have a very resonance stabilized species that has an aromatic and then the positive charge as well. So this benzylic cation occurs all the time, and it's really indicative of having a benzene someplace in our molecular structure. If we don't have, whether or not we have double bonds, lone pairs are actually even higher in energy than those double bonds in most cases. So if we have something like a halogen, we know that we can tell that we have a halogen from the mass plus peak and the mass plus 2 peak. We talked about that in the last section. But we can also tell because we have very particular types of fragmentation. One of the main types of fragmentation that we see with molecular ions is the releasing of a halogen radical, which is actually relatively stable. And we form substituted carbocations, which are also stable. This happens through a process called heterolytic cleavage. So instead of splitting this bond equally right here, we actually take both electrons and move them onto the chlorine, leaving the chlorine as a radical, which again is relatively stable, and leaving behind a tertiary carbocation, which is also fairly stable. Notice that gives us our base peak here, but it's not the only peak that happens. We also see 77 is one of our peaks. And notice that it actually has a mass plus 2 peak in decent ratio. So there's a good chance that it actually has a chlorine on it as well. So we don't always lose the chlorine, but it's one of the more likely things. We can have alpha cleavage with pretty much anything that has a lone pair next to carbon bond, but that's actually the only thing that we see with nitrogen. We don't really see much of anything else. When nitrogen has one of its lone pairs ejected, we end up wanting to form a double bond so we can stabilize that positive charge on nitrogen. Nitrogen really doesn't mind having a positive charge. You know that ammonium, NH4 positive, is a really common thing to form, or amines become ammoniums biologically. So because of this really high stability of this ammonium having a positive charge on nitrogen, this is a really common pathway. Notice what actually happens if we call this the ipsocarbon, the carbon of the amine itself. Any one of these alpha carbons can be cleaved off. That's why we call it alpha cleavage. If we had a longer carbon, we'd see a larger difference between the mass plus peak and the base peak. But notice that any one of these is 15 in this case, and so those are the 15 that are missing from the mass plus peak. In theory, we could have the same type of cleavage for oxygen and an ether. We could stabilize the positive charge on the oxygen, but oxygen isn't as stable with a positive charge, so we see less of a fragment from alpha cleavage. When we have alcohols, we actually get some alpha cleavage. That's definitely a product that happens. We don't see a ton of it if we just have hydrogens, right? So we see a little bit of, we can alpha cleave off a hydride. That's some of the peak that we see. We also don't actually see a lot of the mass plus peak. It's a lot more common for us to actually cleave off the oxygen itself and lose water. So we often see a minus water peak, which is minus 18 from the original molecule. That's possible because the oxygen can pull off a hydrogen if it's close enough. It tends to pull off at the alpha beta position, right? So that can happen intermolecularly. It was 5 bonds away, so you can form a ring. And when that happens, then we are able to form a mass peak that has water ejected, which is pretty normal for a real high temperature. It can't go back once that happens. And then we have this other ion peak. That ion peak can further fragment, but that ends up being a really common peak that we see with alcohols. So when we're looking at these different functional groups, this is absolutely not a memorization type thing. It's a type of thing that you want to use to be able to look at a spectrum and say, okay, if I think I might have an alcohol, what types of things might I see that can be predictive of that alcohol? So if I can find where my mass plus peak is, then I'd look for a peak that's 18 lower. That would indicate to me that I probably have an alcohol. But what I definitely don't want you to have to do is say, like, I need to memorize exactly how this forms every time. That's always something that you can go back and look up. If you have access to a mass spec, you probably have access to your notes. When we have carbonyls, those non-bonding electrons can act in a very particular type of way and also do a type of alpha cleavage. That alpha cleavage can be stabilized through a resonance that has structure that has full octets, just like with nitrogen. And so we form an acylium ion when that happens, having the triple bond between oxygen and carbon stabilizing the missing electrons. That ends up being really quite stable, and so some of our major peaks end up being from that. Notice that we have a peak at 43, that corresponds to the acylium ion. We can also have peaks that correspond with fragmenting off other pieces. So if our mass plus peak is 100, 85 is from fragmenting off this piece, it's 15 lower. We see a peak at 71. Notice that's 14 lower than the 85, so that it pulls off the additional CH2. We see a peak at 58. That's actually going to come from fragmenting and deprotonating, so we'd actually end up with some resonance. So we'll talk about that 58 peak a little bit more, because it's, again, one off from the 57 that we'd expect if we actually shave this off directly. That 58 peak comes from what's called a McLafferty rearrangement. The McLafferty rearrangement is an intramolecular rearrangement that gives us completely stable molecular species, right? There's no charge and no radical on this, and a radical cation that can be stabilized through resonance. If we move this single electron down, we moved another electron up, we could have the electron shared, the single electron shared between the OH and the carbon. That ends up being really, really stable, and so we see significant peaks associated with this. This happens from a lone pair on the, or so not a lone pair, one of the bonding orbitals picking up a hydrogen at the gamma position. So if this is the position of the carbonyl, alpha, beta, gamma is the third carbon out. That can pick that up, and we lose the bonds to the hydrogen. It's essentially an intermolecular hydrogen exchange. As we move those electrons down, they can go into double bond as long as we kick out something else. That gives us our stable molecule, and then we end up with the alkene here that contributes to the resonance with the radical. Again, I want to highlight that when we're looking at these molecules, we're not looking at them for memorize this pathway. Don't memorize how the McLafferty rearrangement works. But if you think you might have a ketone, try to go back and trace back how would the McLafferty rearrangement work for that ketone. Look at these notes, try to figure out if we can figure out how we fragment between that alpha and beta position and what this fragment would actually have a mass for. If you can do that, then you can actually trace back any one of these things to see how you'd expect them to look.